Um, these two questions also continue in the same spirit of properties of the measurable functions. So the first one is easy because it follows the one that we did before. Okay, so what happened is this is typical in measure theory and techniques, I mean, of integration as well. So what happened? You have a function which is defined on a smaller set and you want to extend it to the whole R, okay? And one way to do this, so you have a function defined on a set D, and what you want to do is extend it. So this is your function f, and you extend it here by putting 0. So that's G. So you put 0, 0 here outside of D, and f is equal inside D. So this is a way, so you have a function f defined from D to R, and you extend it to a function defined from R to R, okay, in a very natural way. Okay? So you want to show that f is measurable if and only if G is measurable. Okay? So f is measurable if and only if G is measurable. So this is a very simple exercise coming from the previous one, the one we did before. Why? Because what you do, you consider A is D, okay, and B is the complement of D. So since D is measurable, its complement is measurable, therefore A and B are both measurable, okay? And if you consider G restricted to A, that's exactly F. And G restricted to B, that's exactly the identity function or the constant function equal to 0. Okay? So, obviously, we know that G, from what we have seen this before, that is measurable if and only if GA and GB are measurable. But we know that the constant function 0 is measurable, therefore, if and only if GA is measurable, and GA being equal to F, this gives us the answer to the question number 1. So now we go to question number 2. So we want to show, so one way is easier. So you want to show that every time, first of all, you have function f defined on a domain which is measurable. So we assume that E is measurable. And we want to show that f is measurable if and only if and only if the inverse image of a Borel set is measurable. If a Borel set is measurable. Okay? So one way is easy. We have seen before that if you look at, so here, assume that f inverse of a Borel set is measurable. Then in this case, the answer is easy. Why? Because since if you take the open interval C plus infinity, this is open, so it is Borel set. Okay? Therefore, the inverse image of C, the open interval, is measurable. Okay? Which means that the set of x such that f of x is greater than C is measurable for any C. So f is measurable. Great. So the converse now, assume f is measurable. Okay, so now we know that F inverse of any open set is measurable. Okay, so note from some of the properties of the inverse. We know that number one, F inverse of the complement of a set A is F inverse of A complement. Two, we know also that F inverse of the union of ANs, countable union, is the union of F inverse of ANs. This is just properties from set theory and basic functions, okay, defined on set theory. So with this, we see that the family A such that F inverse of A is measurable, okay, is a sigma algebra, of sets which contains the open sets. Because the inverse image of an open set is measurable. So this tells you what? That it contains all the Borel sets. So this family A, so A contains the Borel set. In other words, the inverse image of a Borel set is measurable.